Okay, so this is a short video about the experiment on the Venturi apparatus. Okay, so we have a centrifugal blower attached to a plenum chamber, which I've talked about in a previous video on the flow around the bend apparatus. And then we have a module attached to the plenum chamber, the exit from the plenum chamber here, with a Venturi. So this is a configurable Venturi. It's a chamber with these two white liners here. So if you look at the manual here, you'll see, I think you'll get dimensions for those liners. It's worth noting that this is, I think, referred to in the manual as the liners reversed configuration. So you can set these up either way. You have the narrow section here. So this is the kind of typical Venturi shape. Excuse me. So in this case, you have the air coming from the chamber in this direction here. It comes out at a particular cross-sectional area out here. So you have a kind of wide height here. And it gets narrower as it goes along, and you have the narrowest section of the Venturi here. The throat of the Venturi is here. Okay, and then it widens out again as it exits out to atmosphere. I believe this is what they call in the manual the liners reverse configuration, where the throat section is about 100 millimeters from the exit over here out to atmosphere. You can also set it up the other way around, where you have the narrow section closer to the plenum chamber. Okay, so what we have here is, and it's a constant width all the way along. So it's just that height difference that gives you the difference in cross-sectional area. So what you find with a Venturi like this is that you have a certain volume of air exiting the plenum chamber. So that'll depend on the fan speed and so on, but you'll have a certain volumetric flow rate of air coming out here, so many meters cubed per second, or a certain mass flow rate, so many kilograms per second of air coming out of this thing here. That's a constant. So for a given fan speed, the amount of air, the flow rate of air coming out of this thing is a constant. But what you'll find is if you decrease the cross-sectional area, the continuity principle kind of tells you that you have to have the same amount of air exiting the system that you have entering the system. But what can change if you change the cross-sectional area is you can change the velocity of the flow. So what you'll find is you have a certain quantity of air leaving the plenum chamber at a certain velocity. As it goes through the narrower section of the Venturi, you have the same amount of air going through a smaller cross-sectional area, so it has to go faster or a higher velocity in order to get the same volumetric flow rate through a smaller cross-sectional area here. And then it widens back out again, so the velocity will drop again as it leaves, or as it gets larger cross-sectional area along this section here. And then it goes out to atmosphere. Now what we want to do is we want to measure that velocity of the air and measure the pressure at different points along the system. And the instrument we're going to use to measure those velocities and to measure those pressures is what's known as a pitot-static tube. So I'll just pause the video for 1 second now. We'll have a look at that. Okay, so this unit here is what's known as a pitot-static tube. It's a very simple measuring device. It doesn't have any moving parts. What it is a tube with two different pressure tappings in it. And those two pressure tappings, you have air lines coming from those to your manometer, and we're simply going to read off two pressures with the manometer. Now hopefully we can get this on camera, but if I look at the pitot-static tube, so essentially it's two tubes, one tube within the other internally, and then those two tubes you can measure them off separately. But at the front section of it here, and hopefully we can get this to focus, at the very, very front of the pitot-static tube, you have one hole, if this thing will focus. Okay, I'm not sure how well that's coming out, but at the very, very front here, there is one hole that's open at the front. Okay, and that hole is going to be pointing directly into the airflow on our Venturi. So how we're going to use this is we're going to insert that into the Venturi, and we're going to use the piezostatic tube to measure the flow rate, or rather to measure the pressures and to measure the velocities. Okay? So that one hole in that little brass cap on the front of the piezostatic tube, that's going to measure the pressure directly facing into the flow of air. I'll try that again and see if we can get it to focus this time. Okay, so we've got one hole facing directly, I suppose, axially along the length of the piezostatic tube. Now what you also have then a little bit further back, so about maybe 30 millimeters back from that point. Let's see if we can focus on this. Here. So just at this point here, we have a number of holes that are pointing radially out from the tube. So if I rotate that around, it's kind of hard to see on camera, but there's tiny, tiny little holes that are pointing radially outwards. So they're at 90 degrees to the airflow. So when this thing is in the Venturi, hopefully we can see that there. When this thing is inside the Venturi, you have one pressure port that's facing directly into the airflow. So the airflow is coming in this direction towards the piezostatic tube. You have one port directly at the front of that little brass cap, and that's facing directly into the airflow. Okay, so that's going to measure all the pressures within the system. It's going to measure the static pressure, it's going to measure the velocity pressure as well simultaneously. And that's what's known as the pitot pressure, that pressure that this one measures, and we'll measure that on the manometer. The other ports then, let's say if I rotate this around a little bit, hopefully you can see those little pinprick holes in the outer radius of this, the outer circumference of that tube. So there's an inner tube and an outer tube essentially. The forward-facing port is connected to the inner tube, and those little small holes are connected to the outer tube. Okay. Now those ones are at 90 degrees to the airflow, so they won't measure any of the velocity pressure or the force of the air pushing against them. Those ports only measure the static pressure. So the port at the front measures both static pressure and velocity pressure. The ports at the side only measure the static pressure. So you can use those to kind of demonstrate Bernoulli's principle that says that at any point in the laminar airflow, that the sum of the velocity pressure and the static pressure should be a constant. So what we'll see as we move this to various locations along the Venturi, you'll see that the velocity pressure varies wildly, but that the sum of the velocity pressure and the static pressure remains more or less constant. Now there's some effects as it starts to exit into the atmosphere here, and there's some effects where it's coming from the plenum chamber over there. But that's the basic idea. Okay. So what you can use that for is you can use this if the front one, the pitot pressure at the front measures both the static pressure and velocity pressure. The ports at the side here only measure the static pressure. So if you take one away from the other, that'll allow you to work out what's the static pressure at different locations along the system. So you can measure the velocity pressure at different locations in the system, the static pressure at different locations in the system, and that'll allow you to kind of plot out graphs of the pressure distribution and also the velocity profile at different points in the system. Okay, so what I'm going to do now is I'm going to run this at a given fan speed, and I'm going to move the piezostatic tube to different points. So I'll say I'll go at increments of 30 millimeters. So if I want to measure the pitot pressure at 30 millimeters, and then the static pressure at 30 millimeters. What I would do is like this. If you see, there's a scale at the front and a scale at the back, so I'm lining the camera up with, get the 30 in line with the 30, it means I'm looking straight in there, or the 3 in line with the 3 centimeters. So to measure the pitot pressure at that location, what I would do is move the pitostatic tube till the front port is just in line with those 2-3 centimeter marks. Take my reading at that. To measure the static pressure at that location, I would move those pressure ports until they're just in line with the 3 centimeter mark. Okay, and then I'd repeat the same thing for, say, 60 millimeters. I'd get in line with the 6 centimeters here, and then measure the pitot pressure at that location, and then measure the static pressure at that location. Okay, so I'm going to run the fans now, and we'll see what happens. So we'll go back to the 30 centimeter mark here, maybe. So get in line with the 2-3 centimeter marks, and we'll measure the pitot pressure at that location. Okay, so the airflow is going out of the thing there. If we look at the manometer, you see here, I'm connected to my plenum pressure is measured here. This is opened atmosphere, this is opened atmosphere. This one with the black tape on it is that's the outer tube, the static pressure is pointing radially outwards. And this one over here, without the black tape on it, that's my pitot pressure facing directly into the air. And you'll see that one here, you've got a very, very high positive pressure. So that's facing directly into the airflow, and you've got kind of all the velocity pressure plus the static pressure there. And the static pressure is very, very slightly different. But what you'll find is that as you move to different points in the Venturi here, so as I move the pitostatic tube to different points in the Venturi, if you see what happens to the readings here, so remember this one is static pressure, this one is the pitot pressure, the forward facing one. Get this to focus. Go. So as I move the pitostatic tube, you see that the change in the static pressure is fairly dramatic. So I'm up close to the plenum, chamber there. We've seen a positive pressure for the static pressure. As I move through the Venturi, so I'm looking at the static pressure here is this one. As I move into the small narrow section of the Venturi, that starts to go negative. So you start to see an actual vacuum in terms of the static pressure. Okay, so that's at about the narrowest section there now. And as I move away from that, I'm back to kind of atmospheric pressure. And if I remove the pitostatic tube, you can see that the static pressure is more or less at atmospheric pressure. But in the narrow section, in the throat of the Venturi, that actually goes negative. You get a vacuum in there. Okay? But if you keep an eye on the pitostatic or the pitot pressure here, remember this is the sum of the static pressure and the velocity pressure added together. You'll see that remains more or less constant. There is a little bit of change in it. Part of that is down to the sort of change in the level of the reservoir, but it remains more or less constant as we go along. You don't get sudden massive jumps in that as you go through the different cross-sectional areas of the system. Okay? So what that tells me is that the sum of the static pressure and the velocity pressure, so static plus velocity pressure, is a constant. And that is basically Bernoulli's principle in a nutshell. Okay. Now what you can use that for is if you look at the difference between those, if you look at the difference between the static pressure and the pitot pressure, that gives you the velocity pressure. If you have the velocity pressure, you can work out the velocity from that. So pitostatic tube can be used to measure pressures, but it can also be used to measure velocities. So you sometimes see pitot-static tubes, let's say on the front of an airplane, to measure airspeed, relative airspeed, that kind of thing. Okay, and you can hook those up to a manometer, or you can also hook them up to an electronic pressure gauge. Just shut down the fans there. We'll just have a quick look, because there is another pitot-static tube that's used on the wind tunnel. Okay, so the wind tunnel chamber here, I'm going to do a separate video on the wind tunnel chamber, but the wind tunnel chamber here, you have an aerofoil with pressure tappings in it, and those pressure tappings connected to a manometer. But you also have back here, and it's inside the chamber, so we can't really see it very well, but this L-shaped tube, here is a pitot-static tube. So there would be one forward-facing port and also some kind of radial ports on that as well. And those are connected here. Okay, so you have your pitot pressure and your static pressure, and those are connected directly into a digital pressure gauge here, which has a calculation on it that it'll actually convert the difference in pressures there into velocities in meters per second or feet per minute or whatever. So you can read it as an actual pressure difference in, say, pascals, or you can convert it into a velocity in meters per second. Okay, so you will be using that in the wind tunnel experiment as well, but I'll do a separate video on that. Okay, so that's the end of the Venturi one. I'll post some data for the I'll post the data for the manometer readings in millimeters at various locations along the length of the Venturi. Okay.